So we now having our next speaker is also joining online from North Carolina, Professor Helen Huang. He's a professor at North Carolina State at the University of North Carolina at Chapel Hill. Yes, I see her. Hi, Helen.
Hello. Can you hear me?
Yes, we hear you.
Okay. All right, can you see my slides?
Yep. Now we have you. Thanks.
All right. Well, thank you, Max, for inviting me. Just a little bit about my lab, what I do. So I lead a lab called Neuromuscular Rehabilitation Engineering Lab. So in the lab, we work on multiple technology, trying to merge human and wearable robots to improve quality of life for people who has a physical disability. So you might have been aware some of my work related to decoding neural machine interface to control prosthetic arm and the legs. And I also work a lot on the artificial intelligence and automation for control prosthetics and exoskeleton, including my recent work using the reinforcement learning for toning multiple prosthesis components control to personalize the device. And of course, because I'm working on this, the human device interface, understanding how human robot interact and also co-adapt with each other is very important. Just like what Elliot shows, we do this fundamental understanding and inform our control mechanism. And using the control, we would understand the science further. So in this talk, I will, because time limited, so I only focus on my current work related. So actually, for a long time, I work on this topic in the neural control of robotic lower limb prosthesis. You might have already seen this multiple times. So current device prosthesis, transition from passive device to the powered robotic device. There are many already commercially available, including also Power Knee and currently Autobot in Power. And then this control, hopefully you also have been go over with some previous talk, is basically the current commercial device and the many prototype is actually using this called a finite state machine. So they generate a different state that basically defined based on the gate phase. And then based on each gate phase, they will describe the mechanics of the prosthesis, such as using the impedance control in this case. And then with the overall goal is to generate this normative walking pattern. So this type of control has been used for many devices. And then here, the circle that I'm showing here is basically represent this state machine. So if you work on the level ground walking, then you need to generate, one circle, one state machine for level ground walking. But if you including other tasks, you have to re-describe this, pre-program the controller to describe the new behavior of the device. And you can continue expanding that depending on how many tasks or locomotion mode you wanted to support for the patients. So the limitation of this control is, one is a lack of adaptation to the environment. Clearly, if the person want to change from level ground to stairs, then if there's really nothing currently in a prototype or I would say commercial device, just don't have that. So usually they generate some manual toning, adjustment approach, like using some certain body motions or maybe just a key fob. And also the other one is this, state machine cannot allow the user to use this device to support a task beyond what is already predefined in the locomotion mode or the state machine. So for example, if the person wanted to perform a task like play tennis, you just can't pre-program the entire, the state machine for that entire game. So because of this autonomous control has a lot of benefits, but you also see the limitation. So I think maybe including the neural control would be an answer potentially can further advance these robotic devices function through this connection with the human nervous system. Specifically, what I'm working on is just using the neuromuscular signal directly collected from the residual limb, so EMG. And I have using a two approach. So I will quickly describe one of the approach that I done many years ago. This is a supervisory EMG control. And then the other one is more recent. We published a couple of work just using the EMG directly, continuously modulating the dynamic mechanics of the prosthetic joints. So the supervisory control, the idea is basically you took the residual muscles activity, and then the output using a certain machine learning approach, and then you can estimate for the next step, what is the locomotion mode the person wanted to perform. And if you have that information, so then you can send it to this state machine to transit between the tasks. So the concept is pretty straightforward. And then I initially using this phase-dependent strategy applied on the EMG signal, and then later extended to fuse EMG as well as the mechanical sensor that hook up in the Prosthesis together to predict the locomotion mode. Just to fast forward, there's a couple of years we made it work in the real time and then control the device. And then probably you have seen this as well, that the user would be able to just transit terrain or locomotion mode smoothly, seamlessly, without stopping or using other body motion. And so the thing that I wanted to talk about is I also see some limitations of this control. So one is, there always has errors in the decoding. So we did a systematic study by understanding the prosthetic error and also the time delay. In these two papers describe that, and then we actually study how that influenced the amputee's stability. So what we realized is some of the control error, even you inject it into the device, but you won't be able to see anything, and the user doesn't feel anything goes wrong. So not all the error will cause the person has disrupt the user's stability. But we also had many errors that you can see. For this one, the video, you can pay attention to when the error show up. So you can see there's like a sudden hyperextension that are causing the person moving forward quickly. So that's a really disrupt the, at least the AP direction momentum in this case. So, and then the user also feedback saying that this, error is kind of feel unstable. So we call it a critical error. And then through these two studies, we have actually quantified the characteristic of these errors. So what errors can be classified as a critical error? And then in the future work, that definitely needed to address these critical error or delay to make sure the system is safe. So, all right. And then another, although, the supervisory control is great for achieving the, the environment adaptation, but talk about other tasks. Remember the second question that I have for the state machine is that they can't perform, the user cannot use the device to support the task that is not pre-programmed in the state machine. But supervisory control is actually built upon this state machine. So it's still, even though you have these, the supervisory control, you just can't extend to the other task. So now then come back to, what if just purely for this task, like, some user just want to lift up heavy box, right? So how do we control the prosthetic ankle? If we think about autonomy, you need to understand the user's state and also the environment, like how heavy is the box, what's the compliance of the surface, the ground surface the person is standing on. It's just a very challenging control. But what if we can, mimicking the human biological system that just using their muscle, right, the residual muscle activity that's supposed to control, manipulate the ankle mechanics, now using that muscle signal to directly driving the prosthetic ankle. So we are generating this, basically we give up the entire state machine, and then we're just using the EMG to continuously adjust to control the prosthesis. And then we are hoping that if this work, it would extend the task that this device can support. So there's no limits, or like no any limits on certain tasks. So we actually did a multiple study just all the way come to here because of my time limit. So I'm going to show you, we have started to working on using the EMG control prosthetic ankle directly. And then there's two control the ankle. One is driven by pneumatic muscle. So this pneumatic muscle function just like a muscle, right? It's active and then it will shortening and generate the force. And then this pneumatic muscle basically mimicking the function of tibialis anterior, so TA. And this muscle was mimicking the function of a gastra. And then we can use the EMG to proportional control this two activity of the pneumatic muscle and then drive the ankle to move. And then we also designed electromotor prosthetic ankle. And we can using, so in this case, we just using the virtual muscular skeletal model to build up this controller and then predict the torque and use that torque to drive the joints. And then the other one is the task selection, okay? So we started with the standing posture perturbation, standing stability, posture stability. And then we given the expected perturbation. So the reason is, right, so there are anticipatory posture control, which is voluntary, right? So when you see something gonna come to you, like a ball gonna hit you, you already prepare for it. So this is anticipatory. Imagine user autonomy. This is very difficult actually to adjust the control in this case. And then also compensatory, when the ball hits you, and then right, so you're gonna react to it. So there's a two stage. So we wanna see, how the person would generate anticipatory and the compensatory control through the EMG control of that ankle. And then we set up an experimental system. The lights, the LED is showing when it's off, means the warning the person the perturbation is coming. And then we can adjust the weight of this ball to determine how big is the perturbation. And the perturbation could be either pull or push, so bidirectional. Okay. So this is how it'll work. So you pay attention to the ankle. So when when lights off, and you can see the user will using the dorsiflexion to stabilize after giving the perturbation. All right. So I'm going to show you the comparison of this approach when we applied on amputee. We actually conduct a couple of study on a couple of amputee already. So this is a person using the passive device with this perturbation. And so we know for standing posture, right? So usually if it's a small perturbation, we usually start with the ankle strategy. Then hip. When it's large enough perturbation, we might use the step strategy. So this is a person using the passive device with this perturbation.
Yeah, I think it's separate depending on.
So as you can see, he has to really use the step response, the strategy to stabilize himself.
Like force with that.
Okay, and then we also, this one is showing you the EMG control, the power Prosthesis. And it's the same magnitude of the perturbation for this person. And I want you to pay attention when the lights, right after the lights off, you can hear the sound of pneumatic muscle, so which is anticipatory. Actually, it started to use that right after the lights is off. And then, yep, I need to show you. And then pay attention to the ankle movement as well.
And to feel with
this is just feedback.
So I'm going to stop here. He's very excited about this. He talked about how he used the ankle is helping him to stabilize himself. So you can see he used the ankle strategy. I don't know if you can see the ankle is actually a little bit of dorsiflexion after giving the perturbation. And you hear, so I hear the sound of pneumatic muscle really like even before the perturbation was provided. So that means that he used the ankle even during the preparation period. So this is just to quantify to show you, you know, how he used the ankle. So if you look at the overall center of mass or center of pressure, so basically consider bilateral full body. Actually, for passive, this side is a passive device, and this side is EMG controlled power device. So actually, they are pretty much the same. So everybody using the anticipatory posture control as well as a compensatory. However, the strategy they're using to do this is different. So if you look at the ankle torque, right? So the gray line is the intact side, and the red line is for prosthetic side. For passive device, he just can't generate torque, which is obvious. But with the power device, he would generate almost the same synchronized activation of the torque. And then if you look at the bilateral AP direction center of mass excursion, and then you can see that for passive device, he can't modulate that much in the passive, but he would be able to do it with the neural control. What is the most interesting one is actually this plot. Is showing the hip angle, knee angle, and the ankle angle during the perturbation. So with the passive device, the user is actually using a lot of hip. So the red, you can see the red color is the prosthetic side, using the hip on the prosthetic side and the knee flexion, okay? But when you use the neural control, and then the hip doesn't move that much, just like the intact, and then the strategy is a shift to the ankle. So basically he shift from using the hip strategy to the ankle strategy. This is a lot. That means he has more resource to stabilize himself. He would be able to use that ankle. So currently we are working on this motorized device. Currently it's still focused on the mechatronic and then figure out the control. So this is applied on able-bodied person. It's using the virtual muscle skeleton model and then drive the prosthesis ankle. Here, just a demonstration of what we did. Okay, well, so the future is one thing that is really interesting, right? Mimic the upper limb folks working on sensation as well. We are asking, you know, for a person, if they, you know, when they wear prosthesis, they lose the actual state of what's going on with the device. If you can restore this actual state, giving some person some idea of what a prosthetic foot is doing, would that enhance further of their motor function? Well, we haven't closed the loop yet, but I want to show you, you know, we have tried some of the neural stimulation, but this is a non-invasive, this is transcutaneous stimulation. And we would be able to hit multiple places, like the toe or heel of the missing limb was filled by this stimulation. And then also we had a very last chance to actually hitting the heel. I don't know why, maybe because it's a transcutaneous, so stimulation. But you know, we're definitely interested to learn more from the invasive approach, what it generated out of their stimulation study. So with that, I want to thank everyone for your attention. And then I do want to emphasize, I think autonomous control is very important. It's working really well for those locomotion tasks. But I also think the neural control has its potential to expand to provide added function into the for patients who has a lower limb amputation. Thank you.
We have one question, Helen, from the audience.
Yeah, one of the viewers would like to know if we use inertial sensor data alongside EMG data for control.
It's for the locomotion mode.
For the
which control is it, direct or?
For supervisory control.
Oh, for supervisory. Yes. So we tried IMU. We also used the load cell previously. Yes.
Thanks.
Great, thank you. I might have missed that, Helen, but the ankle that you're using, is that a prosthetic you develop, or?
Yes, that's what we build our own. I would love to use. Actually, I tried to work with Elliot. We should continue discuss Elliot.
to be continue.
Yeah, and also Elliot's work is very close to one of my work on the reinforced learning control, the toning device. We are also using the user's preference as well, so we should chat.
Great. Well, thanks a lot for joining us, Helen.